Hey Redis geeks, give a big welcome to the creator of Redis and the leader of Redis open source community, Salvatore Sanfilippo.
Hello everybody, and thanks for attending, because usually I pass all my day in Sicily. I work from home, so I'm kind of disconnected from the user base. There are days that I say, but I write all this code, but what happens with this code I write? Because users at conferences will tell you their use cases, what they do, but never an email. Just when they get troubles or stuff like that. It's very hard to receive an email like, I'm just doing that. So from time to time, even with the big cost of the jet lag, it's a good idea to fly and get in touch with the community of users. Because after all, open source software is something that developers do for other developers. So sometimes it's better to get together and talk and have good feedbacks. And in this first talk, I want to talk to you about Redis 3.2. The interesting thing about open source is that it goes forward. Year after year, if there is the drive, the focus, the project gets better and better. So 7 years ago, we released the first version of Redis. It was already useful, but with many limits. And over the years, we started to add things after things. However, there was a moment in the history of Redis when we start to focus a lot on the internals. And the API, that's what developers see every day, remained a bit frozen in a given state. We improved the way the API was implemented internally, but it remained too much the same. There were no new data structures, no new features. And finally, with Redis 3.2, we changed it. We tried to provide new things for the developers to use, new exciting things. Of course, also, less memory usage is very exciting as well. It opens new use cases, but to have new commands, new data structures can be more interesting for developers that can model new use cases. So let's see what's inside Redis 3.2. Probably one of the most interesting additions is the Geo API. Basically, it's you can do a lot of things with geo-indexing. There are many features, and it's also a topic full of complexities, and there are full GIS systems that are capable of doing a lot. We didn't want really to replicate what other people are doing very well. We wanted to model a specific use case. That's what is needed very often in mobile applications. You open your application and you want to see what are the nearest shops of a given type or stuff like that. So basically, the Geo API in 3.2 is the sum of two main features. There are many commands, it's not just these two, but the gist of it is that you can add points in the Earth surface, and then you can ask for what is near this point in this radius, what are all the points that match, okay? So it's really a perfect map for mobile applications and similar stuff. The interesting thing is that this stuff is extremely fast because it's baked by a sorted set internally. What we do is an interesting trick. Basically, you have the longitude and you have the latitude. What you do is to take an integer of 64 bits and you use the odd bits for the latitude and the even bits for the longitude. This may look strange at first, but what you have in this way, it's an index that you can query for ranges, getting squares of different sizes. So when you get a Redis query, you find the 4 squares that or actually it's the then, one the sender and the 9 that are together. You find the squares that cover the area. You fetch all the data and remove the one outside the radius. So it's extremely fast and can be used to model a number of use cases. The second feature is a very odd one because it's low-level stuff. It's called bit field. Do you know what is a bit field in C? When you declare a structure, instead of using the CPU word, like 32 bits or 64 bits, you can say, I want to declare an integer that's just a signed 5 bits integer, for example. Bit field is the same for Redis. So you have basically a string that's an array of bits, and you can use this whole string in order to store counters. Redis had already the commands in order to set individual bits, to get and set individual bits in bit operations. And users exploited this ability in real-time analytics in very interesting ways. However, this is definitely the next step, because you can set an integer with a given size in any given offset, not a ligned, and it means that, for example, if you need many counters, you can store a lot of counters in memory in little space. So it means that you can do tendency analysis and you can track the user behavior in many ways using little memory and using counters that support increments, decrements, or get and set. An interesting thing that's not shown here in this slide of the bit field is the fine control of over the overflow behavior. For example, you can ask to the increments to use what's called saturation arithmetic. That means when you arrive to the limits of the integer, the max value it can represent, or the minimum, stick it to it. Don't wrap around. Otherwise, I can ask to return an error during overflows, or I want it to wrap around. Usually in C code, for signal arithmetic, overflows are not defined. Instead, the bit field command provides a very specified overflow semantics for this use case, and it makes much simpler to work with. And then there is the Lua debugger. Lua is a feature that was very useful to Redis developers in the latest 2-3 years. It really exploded. But the problem was that when you have to write the one-liner script, okay, it's easy for everybody, and if it's broken, you poke with your editor and eventually it works. You don't never know exactly why it works, but who cares? And you put it in production 5 minutes later. But when you write very complex scripts, it's starting to be a bit complex because there is the Lua script and also the commands that return values from Redis, and it's very easy to understand, don't understand anything at this point. So we needed a real debugger. And the interesting thing is that you don't just want a stepping debugger for Lua in order to debug Redis scripts, but when a given line is executed, you also want to understand what's the chat between the Redis server and the Lua script. So for example, this line executed a get operation, and I can see in the debugger that it was get foo and the reply that the Lua script got from the server. So now, and there are breakpoints and the traces, so the kind of features in order to make, and also colorized output in the terminal, that's very important. And so now, writing complex Redis scripts got a lot simpler. There are other important features. Those are the non-user-facing features, no? One is better cluster. Redis cluster was a huge hit when it was released stable with 3.0. Basically, what happened is that the Redis group, the GitHub issues got monopolized by Redis cluster. Everything is about Redis cluster, like if the other Redis that no longer exist. And there is a lot of work to do, but with this release we added, for example, automatic rebalancing between nodes. If nodes start to have uneven amount of data, you can even it again. And also the replica migration, it was improved, so now if a master remains orphaned without slave, there is another replica that will migrate back to the master and stuff like that. This was improved. It was a feature already existing, but it's now better. Scripting now has the ability to control the replication. So I can say, for this script, instead of replicating the script itself to the slave, replicate the effects of the script in terms of Redis commands. And this makes you able to write scripts with side effects, like checking the computer time, but having the same effects on the slides, on the slaves. Before it was not possible, now that's possible. RDB file improvements. Basically now in the RDB file that Redis saves on disk, there is metadata, like the server that generated it, how many memory was used when the file was saved and stuff like that, and you can inspect the content. And also it's a lot faster to load the RDB file in memory because of these changes. Because now inside the RDB file there is, before every loading section, the size of the hash table. So instead of resharding while loading, the server resides the hash table before loading, and it's much faster compared to before. And now it uses less memory, and also Sentinel is more scalable. It's not possible to, for example, use 3 Redis Sentinel cluster in order to monitor 100 masters. In the past it was not scalable enough. Now it uses shared connections between Sentinel and masters, and it's way better. This release took 1 year, and basically it's starting to be a constant in Redis to use 1 year every new release. Now, it's not that super bad or something like that, but it's a lot of time that I want to change this, to have more faster releases. Because faster releases means basically that what we write in the unstable branch gets to the user faster, and the user can use it instead of waiting 1 year. And also in this release we were not able to merge everything. For example, there is a very exciting feature in Redis Unstable, that the ability to remove objects without blocking the server. If you have like a huge key with millions of elements, in Unstable you can delete the key and it will happen in another thread in the background. But this required too many changes in the core of Redis, and I was not comfortable with merging it in a release that was going to be production ready soon. Also, Docker NAT cluster support was not merged, but this will be probably merged in the course of Redis 3.2. However, the idea is to change the release workflow, to work less time to less features and ship a new version of Redis, like every 3-4 months, in order to have something like 3 or 4 releases per year. What's the interesting bit about this is that we could do like topic releases. Okay, we say no, the Redis community for 3-4 months focus on replication and improvements to AOF. And we just talk about that. Even at lunch, at dinner, or when we go to work out, we just talk about 2 Redis features, like mental illness. And really, in order to bring all the ideas about these topics on the table. And of course there will be the usual bug fixing, the small features that get added, but to focus for a couple of months on a given part of Redis, on a given subsystem. And then provide 2 big features and a couple of small ones, and release Redis, and start again with a new subsystem, then cluster, and so forth. For example, respond to the cluster demand. Everybody is crazy about Redis cluster, but Redis cluster is now production ready, but it's not as strong as it could be. There are features that are missing. So let's focus on Redis cluster for 2-3 months and make a release with considerable improvements to Redis cluster. And another could be replication and persistence. Again, and there are endless topics that we can pick. Threading is a very important one because it's possible to use the cores of the computer without to have the data structures to be thread safe. Just the read and the write system call are burning a lot of CPU cycles. So what we can do is to go them and cache the root. That's basically to just scale the I/O, and when there is to read from memory, there is a global interpreter lock, like the GIL or the Python GIL or something like that. And because fetching the data is the fast part. The slow part is reading from the socket, parsing the command, and then sending back the reply and stuff like that, because you have system calls that, because of the kernel context switch, take a lot of CPU. And so that's the idea. Hopefully we will have a new release in 3-4 months instead of 1 year. Otherwise, even if this will not happen, the important thing is that we keep going, and that after 7 years, new things are added, and the project is very alive, and that's great. I hope it will continue. Thank you.
Ladies and gentlemen, please welcome Redis mad scientist at Rackspace, Bill Anderson.
Good morning. So 15 years ago, I had my first introduction of what we now call big data. The term didn't exist back then. But for that case, I had to deal with 2 terabytes of email log files every single day. And we had to process 90 days worth of this. So that was a lot of data back then. I would say it's still a lot of data today. The catch with this is it had to be searchable very, very quickly. Otherwise, we would tempt the heavy-handed fates of the Exchange Commission. Now, it was this singular experience that set me on the path that eventually led to Redis. Obviously, 15 years ago, it didn't exist. But thinking about it, and the things I learned from that experience still informs how I think about Redis today, what it can be used for, what it can do, and what maybe it should or shouldn't do. For the last 2 years, I've been playing with Redis, with Sentinel, with various proxies, Xcodus, Codus, 2M proxy, in thinking of ways that we could improve the way we utilize data on Redis. And that journey, I briefly summarize, I hope it's briefly, in the idea called platforming Redis. Now, we're all familiar with Redis as a data structure server. But what if we shift our thoughts a little bit and think of it instead, if we wrap the ecosystem around Redis and Redis itself into what I call a data platform. Now, there are key components, key things you need to do to have a data platform. Obviously, in this case, we start with Redis, or ultimately something that looks and acts like Redis would work as well. We're through some creative uses of Sentinel, some mixing in of the hot topic, the magical Docker fairy dust, and some custom wiring to work around some of the few Redis gaps that still exist. Then we can build something that's truly special. So first up, let's address the virtual elephant, the Slack channel. Salvatore briefly mentioned it actually, and that is the fact that Redis with replication in Docker doesn't play so well together. The key here is that the way replication and Sentinel tie together with Redis is that Sentinel needs to know how to contact every slave. Now there's some work going on in DiskQ and in Redis cluster, as Salvatore mentioned, to address these problems there. And hopefully we're going to bring that into core Redis as well to solve these issues. In the meantime, there are a few things that you can do to get around that. The key thing with Docker is the port translation. Redis you fire up inside the container on a given port, Docker needs to map that to a port externally. One option is to run custom ports for every instance. In order to do that, for operational perspectives, you need to have something that maps each instance to that port, so you're not reassigning ports, because that can get into an issue. And then the other option you can use with Docker, utilizing the same techniques, is host networking option. And in that case, Docker isn't doing that mapping you're actually using host level sockets. And then there's another option, one that I toyed around with a little bit, working on Red Skull, called Gordo. Gordo is a simple daemon that you run as your Docker containers process, and then it manages Redis itself. So it actually fires it up or turns it down. And what this gives you is the ability to specify the ports after your Docker instance comes up when you have that information available. And that means you don't have to do that mapping. Now, if you're going to do this, and you're going to do it across Docker Swarm, now you've got multiple hosts. One of the main reasons you want to run multiple slaves, or at least a slave attached to a master, is for availability. This is actually really easy to do with Docker. You name each instance with your pod ID or your master name in Sentinel, and then have the Docker Swarm constraint system prevent those from launching on the same one. Fairly simple to do. A lot of people don't think a lot about it. Now, the custom wiring. If you're going to do this, you need to track all that information, and that can be a lot of information. Now, I recommend you use Console for this. Console has a lot of advantages if you're using it to manage Redis and you're working with Sentinel. And honestly, that's such a great topic, it'd be its own talk, so I'm not going to go into those details. One of the other options that I use is a tool called Red Skull. Red Skull is a Sentinel management system, and you can use that to be able to increase the size of your Sentinel constellation. And it's undergoing some refactoring right now, integrating Console a little bit more, and hopefully by the end of summer it will actually be able to launch Docker instances on your Docker Swarm, wherever you have that Swarm running. And if you want to deploy this, from an operational standpoint, pretty simply, you can use Docker Machine. It will actually launch the instances, set up Docker, and then you just build your stuff on top of that. Or if you're a gopher like me, meaning you like to use Go, libmachine will let you do this as a library. You can make APIs, you can make command lines, commands, really easy. Now the Sentinel piece. We're all familiar with Sentinel in terms of providing HA, managing your failover, who's master, who's slave. What a lot of people tend to forget about is you can use it for service discovery. And service discovery gives you the ability to specify any pod, give it a name, and then rather than your client code, rather than your API server or your metric server, having to know where that lives, all you have to do is ask Sentinel. Sentinel will tell you where it currently lives. So that removes that part of the configuration. Now, that's obviously needs to play a key place in a Redis data platform. Now, one of the things we're going to talk about a little bit later is taking the Sentinel piece and extending it. So once you have that, what all could you do with it? So from an engineering standpoint, it gives you the ability to deploy Redis, lots and lots of Redis, anywhere you need to run it. You have a common API. You use the Docker API. If you're over here on Google, running your stuff on Google's cloud, use Docker API, you're done. AWS, same thing. Rackspace, the same thing. Wherever you can run Docker, you have the exact same API. And that's pretty neat on itself. But I think we can do a little bit better. I think we can do more things with that. In fact, you'd be surprised what we can do with that. Obviously, the first thing that's probably coming to a lot of people's minds, particularly given that it's somebody from a Redis provider talking about it, is this gives you the ability to have Redis as a service. Now in this case, however, I'm thinking more of an internal use scenario, where let's say you're a large company, you're running Redis internally, you have different groups within the company, they all want to have Redis servers. You don't want to throw all of those onto one. This would give you an easy way to manage that, to be able to say, all right, marketing wants some Redis servers, let's spin them up for them, easy management. But that's just a start. That's a little bit too simple for me. Well, first thing that I like to go to here is what I call ephemeral Redis instances. Now, ephemeral Redis instance is something that you spin up, you use, and you get rid of. That's a little bit different concept for those of us using Redis. Often, we're using Redis over Memcache because we like the persistence, or we're using Redis because we're going to keep this data. A lot of people do use Redis to keep as their main database. So why would you want to spin it up and then throw it away? Well, think about a testing environment. Continuous integration. If your code interacts with Redis, you have the standard option of let's just have a Redis server always up and ready. Or you can have a system like this, which allows you to spin it up, run your tests, and then spin it down. And that's why I call it ephemeral. There's also some other neat things you can do once you have that type of a setup. So that type of setup splits that out. Now you can have, let's say, scheduled tasks, cron jobs, temporary job instances that need to talk to Redis. Maybe they pass on information to another one, maybe they don't. If they don't, why spend your time having maybe 1,000 jobs, 2,000 jobs, all talking to the same Redis instance when they can each have their own? And I'll get into a little bit later how that brings some additional advantages. But let's take that idea of ephemeral Redis instances and the idea of being able to spin them up whenever we want. Great use of this is in scaling web sessions. I'm sure a lot of us are familiar with putting web sessions, user sessions, into Redis. It's one of the common use cases for it. But this actually creates what I call a virtual single point of failure. Even if you have that Redis set up as what I call a pod, a master and slave replication set up, even then, you still have that virtual single point of failure because a rogue flush all or flush DB means you just lost all your user sessions. Now, obviously with user sessions, that may not be the end of the world, but what if you're storing shopping carts in there? You really don't want to anger your customers. They're trying to buy stuff from you. So this type of setup allows you to expand that and go from one setup doing that to as many as you need. Ways you can do, you can use persistent sessions on a load balancer, or you can go to an extreme of every instance manages one user session or one web session. And that gets around one of the particular weak spots in Redis, and that is the single threaded. You put 10,000 clients up against a Redis server, even ping is going to take a lot longer than if you're running one. And it's kind of obvious in hindsight. Now, the idea of putting of mapping a user session to a single Redis instance kind of starts getting us to think about it a little bit differently and going into a direction that we're not comfortable with a lot of times. So let's go into that. In order to do this, we're going to use Sentinel. Some might say we're going to abuse Sentinel in this particular case, but why would we want to do that? Because what we're really talking about when I say move them across multiple instances is we're really talking about sharding. And very few people are masochistic enough to enjoy sharding their data. It sucks. Anybody who's done it will tell you this. Now sharding, for those who don't know, is when you've exceeded the limits of your single database. Whether it's CPU, whether it's memory, whether it's network bandwidth, whether it's just sheer storage space, at some point, hopefully in many cases, you're going to outrun one. And that's where you split up your data and put it on multiple systems. This gets really complicated really quickly. Sentinel can actually do this for us, but it requires that we think a little bit differently about sharding. Now, if you really think about it, everybody here who has run Redis or run an SQL database has sharded your data. Every single one of us. Now I know some of you are going, no, Bill, I run one. I'm not sharded. Yes, you are. You have a shard of one. Now, however, once you think about it that way, it kind of changes the way you think about sharding. And I think this is an important difference. Because at that point, what you realize is that sharding is a continuum. At one end, you have one instance, one shard, one slot. And at the other end, you have more. And what I call this situation is the granularity of shards. How fine-grained are you getting in breaking that out? A broad-based example might be, I put all my users from each state on their own instance. That's, if we're talking United States, that's 50 shards, done. And that gets really complicated, but that other end of it is where it gets really ugly. And a lot of us have maybe thought about it and went, I don't want to give a shard for every single core object in my system, because that can be a nightmare. If you have 1 million users and you're sharding one shard per user, that's 1 million shards. That's crazy, right? I thought so too, but maybe not. if we leverage Swarm, and we leverage Sentinel, and maybe tickle it in some interesting ways, this may not be such a crazy idea. So let's explore this idea. The first part of that, let's talk about Swarm. No, that's not a real word. I just come up with it because it sounded cool. Swarmification. This is just, to me, it's basic Docker, right? If you run Docker, you run Swarm, you know exactly what I'm talking about. So set up maybe a dozen nice beefy machines or virtual machines, set up Docker hosts on each of them, put them together in a Swarm. Now in this case, a dozen machines, physical hardware here. I was able to run over 9,000 Redis instances. Now that's not a million, but that's a lot more than most of us have ever really run in one place. Now, obviously, we're not talking 1 terabyte instances or multi-gigabyte instances. That's another advantage of running a finer grained shard, is that each shard gets smaller and smaller and smaller. So now, if your user sessions are only a meg, 2 meg, 3 meg for really heavy ones, you can start to see 9,000 is not necessarily a lot of too much memory. But what about Sentinel? How do we do that? Well, the Redis Sentinel docs actually tell you how to do this without telling you that you're sharding. They tell you that Redis Sentinel can manage multiple pods, and it can, and use service discovery to differentiate between them. In that scenario, even though they don't explicitly say it, you're sharding based on function. I'm storing user sessions here, I'm storing my object cache here. That's function-based sharding. Very broad, very coarse-grained. But if we go down to the individual object, let's take a server name. You're managing thousands of servers. You're collecting metrics on them. Every server gets its own shard. This means that you name that pod the server name. Now you have a direct mapping. You don't have to calculate anything. You don't have to run a hashing algorithm. You don't have slots to manage. It's a direct mapping from each server right to the host, right to your data service. This eliminates an entire layer of complexity. It actually eliminates like 80% of why sharding sucks, because you don't have to redistribute things when you need more slots. That makes it easy to scale. If you're doing indexing, generally sets, sorted set type operations, you can put those on their own shards. So now you have your indexing operations out of band. So I threw up an experiment, 3,000 simulated hosts sending all sorts of system information every 60 seconds. I went with a dedicated pod per server, and the pod name is the server name. Ran this on 8 beefy physical machines. This is the overall process it went through. The agent sent to my data service, multiple of the copies of that running, sent it to the server called Palisade, which then gave the information back. And you notice there it says Sentinel Master, it's using the Sentinel API. Results? Well, honestly, I had to run it a few times because I didn't believe them. And I still not kept believing them. Because I'm sure some of you have noticed that number at the bottom of the screen. Yes, that is the correct number of zeros. The system was able to sustain over 450 million commands per second. And yes, that seems like a lot, but in hindsight, it actually makes sense. We've eliminated the concurrency issues with Redis. Everybody gets a direct one-to-one mapping. So you're not competing for those resources, and your limits actually become how fast can you push the data into the platform and how much network bandwidth you have available to do so. During this test, you could fail over any given system. The rest of the system's completely unaffected. You can wipe out an entire service data, the rest of them are still there. Rogue flush alls, no longer a problem. Now, server Palisade. Palisade is something I started writing. It is a partial Sentinel implementation. And by partial, I mean it speaks Redis, and you could implement a full-blown Sentinel with it, but its purpose is actually to serve as a proxy. And what we can do as an intelligent proxy for Sentinel is we don't need the insane speed of Redis. So we don't have to do this in some really tight C code. But it gives you the ability to do full user authentication because you are intercepting the commands. You can take your auth command, you can split it into user passwords, and once you have that, you now have Sentinel authentication That also gives you the ability to do ACLs. So you can say, all right, this user password combination has access to these pods. And that kind of gives us a little bit of a benefit we don't have in normal Redis. And gives us some more use cases. The temporary instance I mentioned earlier, I think can be really powerful to scale your data to ridiculous levels, very large data sets. The ability to scale your cache serving, if that's what you're doing. But it also gives you security and isolation. There are many cases where Redis has not been a good fit because the lack of user authentication, which can be really complicated to implement. By bringing that into a proxy and by isolating every user's data, you can move them around, and my data isn't affected by your data. Your data isn't affected by my data. There are a lot of regulations around, governments do privacy, security, PCI, that type of stuff, where you want to have that information differentiated. You get to do this without being affected on the back end. So that gives us some really neat possibilities, and I encourage you to explore those. Do neat things like, I don't know, modified postfix to store rather than queue files on the file system, put them in Redis, distributed postfix system. This is the repos locations for some of the software I've mentioned. Most of these are pretty well beta at best, but particularly Palisade, you can use to write your own implementation of Sentinel. Very useful for mocking and tests, and for exploring different ways you can use Sentinel. Thank you.
Ladies and gentlemen, please welcome Armakuni co-founder and cloud native developer, Tim Savage.
Morning, everyone. So my name's Tim Savage. I'm from Armakuni. We're based in London. We're a consultancy, and we help organisations sort of change the way they approach problems using cloud-native solutions, approaches, practices, and so on. I'm here today to talk to you about a client of ours as a case study, and to talk about how we view what we've delivered for them. The client in question is a UK-based charity called Comic Relief. So I'll try and give you a bit of information on Comic Relief and try and sort of set the scene for you all. So, Comic Relief's been around for 25 years. I grew up with it. Anyone from the UK will be very familiar with Comic Relief and Red Nose Day. It's a big charity. It's all about being funny for money. These, which I find myself having to explain here, are red noses. They all come in odd shapes and colours now. But originally they were based on just the ordinary red nose that you stick on your nose, and people did it on the day, and that was how it worked. But I've kind of grown up with it. So anyway, Comic Relief have raised over £1 billion now. That's pounds sterling, towards their vision of a just world free from poverty. They primarily operate two campaigns, the Sport Relief and Red Nose Day, and they sort of run on alternating years. We just had Sport Relief in March this year, and there's actually the US version of Red Nose Day is coming up in May 26th, I believe it is. So you might see some of that around. I think Walgreens are selling noses and so on. We support the campaign events, so they culminate in a telethon, sort of a whole evening, 7 in the evening till 2 in the morning, and we take over BBC One. And that's where we come in, because we support the credit card payments behind them. So I've now got a little video I just want to show people, just to give you a feel for what it's about and what the scale of the operation is in terms of the event. So we roll the video? So, the last few campaigns have raised in excess of £18 million. And 90% of the annual public donations will come in during that night, that 7-hour window. So we're processing 8-digit numbers in 7 hours once a year. This creates a few problems. Comic Relief is a charity. They have a tiny budget, and anything we spend that's above and beyond what we should be spending, or getting too far into things, we can see the consequences in terms of £5 from mosquito net. There's no second chance. When the people are out there and they're sort of watching the TV show and they get the urge to donate, it's an emotional thing. It's at that moment. It's kind of gone the next day. It's not like buying a TV and you can come back and, I want that 40-inch TV with the curvature. I'll come back the next day if I can't get it. It's not the same, so we don't have that second chance. We don't get any operational usage, so most organizations get to try these things out and solve problems constantly. We don't get any of that. We get a trickle of traffic through the site in advance. Maybe we might get to a donation a minute, something like that. It operates at significant scale. So we're taking over BBC for 7 hours. It's a big event in the UK. We pretty much will get the bulk of UK sort of TV watchers will hit the program during the evening. So we're talking numbers in the 26 million region. And also brand confidence and reliability. So Comic Relief is all about its brand. I mean, I don't know if you can get that feeling from me, but I grew up with it. It's sort of instilled in you from a child, and it's there and part of your psyche, and everyone trusts it and knows what they do, the good work they do, and everyone gets behind it in a way. So what do we deliver? What are the requirements here? So it's all about being funny for money, but then you get to someone like David Tennant here, who's the Doctor Who, probably not going to mean so much here, but a celebrity, there's one. Celebrity comes on and shows what's going on and how we're trying to raise money and why we're trying to raise money. And onto the screen goes the big number and the website URL. So at that point, people start going online. We operate a fairly simple donation form. It's designed to be simple for the general public. It's cross-device. We try to keep it as simple as possible for us as well, but it's surprising how complex that can get given the wide range of people we have using the platform. But we're expecting in the region of 100,000 concurrent connections, but we're never quite sure what sort of scale we're going to get. We also support an interface for the call center side of things. So when you call that number, you go through to one of the call centers that's donated their time for the night. So there'll be in the region of about 100 call centers across the country, culminating in about 10 to 14,000 operators. And they're all using another web system that we run that collects the money from the people phoning in. So we have a fairly peaky traffic profile. This is an example from a couple of years ago. It's 10,000 donations, so we're talking real-time credit card transactions. In this case, it's 10,000 per minute. So that was a peak, I think, on that one of about 226 transactions per second. And this comes back to the key performance metrics that we have and that we work to with Comic Relief. So in particular, this is the top two ones here, which are what I've pulled out for this slide. We build the platform to handle, without fail, 400 donations per second. So our objective is to take that. Everything else goes out the window. And handle up to 800,000 donations in total. And that's during a 7-hour window, once a year, and no second chance. So I'm going to try and give you an overview of the solution, and then I'm going to go into a bit more detail around from the Redis perspective. So I'm going to just quickly lay out what an event night platform looks like. We use Cloud Foundry. This is what we call a front-end shard. We use the phrase shard. I'm not quite sure where it came from in our term, but it's a shard for us. This one is in US East on Amazon, so it's Cloud Foundry. We operate a microservices architecture, so within this, we've got 29 services running for this platform at the moment. They'll all be deployed into here. We'll only be using the ones that are relevant for a front-end shard for that role. So I think that's 5 of them. This, on its own, will be rated to 400 donations per second. So this can handle the event night. And there's a mix of sort of Ruby apps, queues, workers, and so on. And there's also some Redis instances there, but I'll come back to that in a minute. So we then provision another shard in Dublin. And we also have a shard on, in this instance, vSphere. We also use various other services, so Cloud Foundry services such as BlueMix, and we're talking to at the moment as well. Payments. So, one mandate that Comic Relief has is that they want to be or to have as minimum footprint as possible from a PCI perspective. This is related to cost, it's related to brand, reputation, a whole bunch of things. But that means that we use third-party providers for the actual payment side of things. For us, as soon as we bring one of these guys on board, that's a critical dependency. So as we were doing with the infrastructure providers and we were getting redundancy through resiliency across the geographic locations, we load balance across multiple providers. So currently we're using Braintree, Stripe and WorldPay. And that gives us a combination of performance and redundancy. So in terms of real-time processing. So we're able to process synchronous or asynchronous. So synchronous being where we give you the feedback straight away. Your payments failed for whatever reason, we can tell you at the time and you can try again. And that gets us much better success rates in terms of our sort of failure percentages. But we can also take async payments. So we store the credit card data with one of these providers, keep the token, and then we process asynchronously, and that's one of our sort of failure mechanisms. So coming back to here, we've now got another shard down the bottom, which is what we call our insight layer. So this, again, it has all of the applications deployed within it, but it's looking after all the asynchronous tasks. So asynchronous payments, sending emails, exports, till we push all the data back to Comic Relief as and when it's collated. And it also does collect it all from management reporting and then transaction insight. So this is slightly over the top, but what we're trying to say is that a whole lot can be on fire, having trouble, but right in the middle, there's one shard that's still there, and that will take 400 donations per second. So we can withstand a huge amount of failure or problems, all sorts of things going wrong. We're across all sorts of different providers, services, and so on. We can still take, under all of the scenarios we've tested anyway, 400 donations a second. How do we manage all this? Everything is code. We operate full continuous deployment for code and infrastructure through to production. So we do this all day, every day, all the way through the year. So we're very familiar with pushing to production. So if I make a change to one of those applications up on the top left-hand side, it'll hit production in about 30, 40 minutes. During that time, it'll have been through a bunch of environments, it'll have been through unit integration, feature tests, security tests, load tests, a whole range of things to allow it to get into production. And we're in a position now where we're able to deploy mid-event. So we had a request come in last year for a change during the event. We were taking 40 credit card transactions a second, and we did a blue-green deploy into production. So confidence is high. Load testing. So I can't get away without mentioning it. It's pretty key to what we do. As I was saying earlier, there's no operational usage, so this is the only way we know what's going to happen and how we're going to survive. We do a huge amount of it in the run-up to the event. I mean, most of our work for the 2 months beforehand is creating scenarios, game days, thinking of things that can go wrong and trying to sort of simulate them and get into a position where we can do that. We test ourselves, and we also test the payment service providers that we're using for the services they're giving us. So we get quite involved with them. So typically for us, a load test will consist of 3 main platforms. We're going to build our platform. We build an entirely separate platform to mock out all the third-party services. And then we build another platform to generate the load we need, which is pretty significant to sort of push that traffic through and get to the similar levels. That takes us about 30 minutes to bring that platform up and sort of run a day's worth of game day and then back down again. So that's the platform. Where does Redis fit into all this? So I'm going to try and just go through these slides fairly, actually not after this one. So architecturally, we chose availability over consistency. Our data is eventually consistent, it flows through the system and is all recompiled at the end. And that means from our perspective, we can be taking transactions, but we might not be able to report on it at that point in time, or the reporting might be slightly behind, but that's less important than taking the money at the time when it's happening. We might have a 3-minute window when a large percentage of the money is going to come in. We need to be taking the money. Transaction events or states are stored as deltas that we move through the system. So this is an example here for an asynchronous payment. So at the top, card details are stored. So that's where the customers or the donor has put their credit card details in. We've stored the card, we've got a token, but for whatever reason, we aren't able to process it at that point in time. That goes down through the system, and then asynchronously, we run a payment job against it. then a success email, and then export data. And these are all pulled together in the transaction insight and the management reporting, so it's eventually consistent. And Redis plays a key part in how we move these deltas around the platform. This is our architecture. It's a slightly different view to the one I had before, and I'm going to quickly just sort of remove some of the noise behind it and just distill it down to, I'm back to the 3 shards at the top, which we had, and then the insight layer behind. So I'm just going to have a quick look at one of the front-end shards again. On completion of a transaction, the delta was created. So if we look at the one we had before, the payment taken delta, card details stored delta, that will be stored in 2 memory-backed Redis. We store them in different geographic locations because at that point in time, it's the only copy of that data. It will then be picked up by a worker and pushed down to the API. So generally that data only exists on that shard for a very short period of time. If we start to get queuing there, that's sort of one of the things that we look for. If the app can't push to the Redis, they'll push directly to the API and shut down that shard in entirety. So that's how important they are to the success of these shards. So this is the insight shard. So right at the top left, we've got the API. These deltas are hitting that API. And they then go into a processing loop that we internally call the circle of trust. I'm sure it's got much better names, and there's all sorts of other similar patterns and so on. But I'll just sort of walk you through it. The delta will hit the API, and a job will be added to the input queue. This will then be picked up by a worker, drops the delta into Mongo, which is our sort of eventual store, and then add it into the next logical queue, which in this case, of the example we were looking at before, is a payment job. Payment job happens, and the delta is stored in the Redis. Again, it's dual Redis because it's the only copy we've got at that point in time, so we want to push it into 2 separate data stores. Another worker will then push this up and push it around the system again. So the next thing that will happen is it'll go around and we'll get a success email, a successful transaction, and then finally the export. And all of those being pushed into Mongo for the to be eventually available. Throughout all of this, we use Rescue as the queuing application. So it's a Ruby app. It's a fairly simplistic use of Redis in this respect. We're just storing the deltas in it and pushing them around the system. So just in terms of finishing up, this is one of the dashboards from this year, so from March the 18th, when we ran the sport relief. This is fairly early on in the evening. There's not, it's just beginning to start to pick up. So we've got 5 donations a second going through. It's not much, but it's kind of early stages. And it's the bottom section that I'm interested in. So the top half of that, so it's not, this is how it was on the night, so it's slightly operational, but the top half is the list of all the queues. So that's telling me what's going on at any point in time. And as you can see, there's not much being queued up. We're in a good state at this point in time. Get the odd blip running through, not blip, sort of event running through. They're on fairly short timers, and we're looking for any problems occurring there. And then the lower section is where we've got failures. So we had a bit of a fail in the afternoon with a couple of things in terms of other providers getting themselves ready for event night, and so where we were pushing data through, we were getting some odd errors. So that's what those queues are. I spend my evening watching these queues. It's become my life with Nose Day. So going back to the original title, can you trust Redis to save a life or to save 10,000? I don't think what Comic Relief does can sort of be distilled down into numbers, but as David Tennant said earlier, £5, or the equivalent in dollars, is a mosquito net. With the numbers we're talking about, you can probably do the calculations in terms of what we're generating for the general community. So I know that Comic Relief trusts us to deliver this platform, and we, as part of that, trust Redis to deliver that side of it. We've been using it for 4 years. We have not had an issue. It's pretty much been seamless. So I just want to say thank you to everybody involved. It's much appreciated. Anyway, I'm very proud to be part of it, and I hope you enjoyed the story. Thank you.
Ladies and gentlemen, please welcome founder of Eventuate.io and author of Pojos in Action, Chris Richardson.
Thank you. So in this talk, I'm going to answer 3 questions. What are microservices? Why should you use them? And where does Redis fit into a microservice architecture? But first, a little bit about me. So I got my start in programming back in the mid-80s, building Lisp systems, all the way up from compilers, garbage collectors, runtimes, all the way up to IDEs. Eventually, I ended up programming in Java, and back in 2006, 10 years ago now, my book, Pojos in Action, came out, and that's all about building applications with Spring and Hibernate, which back then were revolutionizing enterprise Java development. And then back in 2007, I started tinkering around with what was then a very obscure service, Amazon EC2. I created an open source project, which then evolved into my startup, which was the original Cloud Foundry. So that was a very straightforward Java PaaS for deploying applications on EC2. 11 clicks of the mouse, you'd upload your WAR file. Cloud Foundry would launch EC2 instances and monitor and manage them. So that got acquired by SpringSource shortly before SpringSource was acquired by VMware back in 2009. I spent a number of years there, and now these days I do everything related to microservices. So I do consulting and training around microservices, and I also have a startup called Eventuate that's building a platform that will make it easy for developers to create event-driven microservices. So that's me. What are microservices and why should you use them? So if I look back, most applications that I've built over the years have had a monolithic architecture. Internally, they were logically layered and modular, but everything was packaged up as a single unit, the monolith. So in the Java world, that would be a WAR file, or a jar file, or an IR file, running on some kind of application server. And for the most part, I'd imagine that many of you are building applications that have a monolithic architecture. There's a good reason for that. At least in the beginning, building applications with this architecture is quite straightforward. They tend to be simple to develop. Our tooling is oriented around building an application. They're fairly straightforward to test. They're also fairly straightforward to deploy. You take the application, the file or the directory, you copy it to a machine and start it up. And they're fairly simple to scale as well. You just run multiple copies of them behind a load balancer. The trouble that you run into is that successful applications have a habit of growing. You have a team of developers every day. They're writing more lines of code, making that monolith bigger and bigger and bigger. So given enough time, you are ultimately going to end up with a large, complex application. And at some point, you're very likely to be in a world of pain, where anything to do with your application is painful and slow, and any notion of agility is just absolutely impossible. And probably meant some of you are in that position today. So the solution is to use the microservice architecture. The big idea with microservices is that you functionally decompose your application into a set of services. Each service is a small application that's focused on performing some particular business function. So the catalog service is maintaining the database product information. It has a search API. The review service is maintaining reviews. The orders service is dealing with orders, and so on. Each one of those services has its own database. That's really important to promote loose coupling. So as a developer working on one of those services, I am free to make changes to my schema without having to worry about impacting any other services. And later on, you'll see that there's some quite interesting consequences of that. Sitting in front of those services is something called an API gateway that acts as a facade. So that exposes an API, a single entry point into the system, and that API could be consumed by web applications like the storefront UI or applications running on a mobile device, for example. So the microservice architecture lets you develop and deploy much faster. Each one of those applications is a lot easier to understand. So as a developer, you're not struggling to understand a large code base. And also this architecture is very much aligned with the notion of breaking up your engineering effort into or engineering organization into a team of teams, where each team is agile, it's small, it's autonomous, and that team is responsible for developing and deploying their services. And all of these teams are actually working in parallel at maximum speed. The microservice architecture also lets you scale more easily as well. So for example, components with wildly different resource requirements, perhaps one that needs a lot of memory, another that needs a lot of CPU, can be deployed as separate services on the hardware, say on the EC2 instance type that's best suited to their needs. So scaling is much more straightforward. The microservice architecture also enables you to pick the best technology for each service, unlike in a monolithic application where you effectively are using the same technology stack throughout. And that will be a technology stack that will become increasingly obsolete. With the microservice architecture, you're able to just pick whatever technology is best suited for that particular service, so you can evolve your technology stack much more easily. That's not to say that microservices don't have their downsides. There are in fact some significant drawbacks, but for large, complex applications, they're usually the best choice. And for that reason, microservices have been used widely, and they're growing in popularity. So internet companies like Amazon, Netflix, and eBay have been using microservices for quite a long time now. And then more traditional companies like Capital One and Comcast and Lending Club are also adopting the microservice architecture. So where does Redis fit in? So and the answer to that is in many different ways. So each service, is an application. And so a service can use Redis for all of the usual use cases, such as caching, as a high-performance database, as a high-performance messaging system. So for example, in this e-commerce application, the catalog service could use Redis as a cache in order to boost performance. Also, you can use Redis for inter-process communication. So for example, the API gateway, when it handles a request for product information, actually has to aggregate data from multiple services. So it has to go to the catalog service, get its data about a product, go to the review service, and so on and so forth. One way to implement that is it could make a REST call to each one of those services. But another more interesting approach is to use Redis pub sub. And the way that would work is as follows. So the API gateway could broadcast a request. I need information about this product. That request would be received by all of the services that know something about products, and then they would respond with what they know. The API gateway would aggregate their responses and then send back a response to that client. So that's a really great way of implementing that kind of use case. And it goes by the name of the needs pattern, and Redis pub sub is a good fit for that. Also, the API gateway could use Redis internally. So in my own product, I'm actually using Redis for rate limiting. It could also be used for caching and also as a high-performance routing table as well. There's another use case that I want to talk about, but before I can get to that, I actually have to describe a couple of challenges that you will face when implementing a microservice architecture. The first one of which is how to maintain data consistency. So if you recall, each microservice has its own database. That promotes loose coupling. But one challenge that you're going to have to deal with is that some business transactions span multiple services. Normally, on a traditional application, you would use distributed transactions or two-phase commit to maintain data consistency across multiple databases. But that technology is not really viable for most modern applications. So in other words, no distributed transactions, no two-phase commit, yet at the same time we need to maintain data consistency. Here's an example of this problem. So let's imagine that you have orders, and then the orders belong to a customer. Customers have a credit limit. That means that when you place a new order, you have to verify that the customer's credit limit will not be exceeded. You have to ensure that this business rule or invariant is enforced at all times. Now, if both customers and orders reside in the same database, that's straightforward. You can accomplish that with a local ACID transaction. But in a microservice architecture, they're very likely to reside in different databases. And so we have this problem of how do we enforce this business rule. So a good way to do that is to use an event-driven architecture. And that would work as follows in this credit check scenario. So when a request comes in to create an order, the order service would actually create that order in a pending state. It would then publish an event saying, I've created an order. That order would be consumed by the customer service, which would perform the credit check and actually reserve credit for that order. If there was sufficient credit, it would then publish an event indicating the outcome of that credit check. Either a credit check reserved or credit reserved event or a credit check failed event. That one of those events would get consumed by the order service, which would change the state of the order accordingly, and then send a notification to the user, the customer. The order has been approved or it's been canceled due to insufficient credit. So far so good. You use events. But there's a challenge. How do you atomically update the database and publish an event? Those two operations have to be atomic in order for your system to function reliably. This is an example of a dual write problem that we would normally solve using two-phase commits. So this is sort of the exact technology we're trying to avoid. So there's a variety of different ways of accomplishing this without two-phase commit. But the one that I like to use is known as event sourcing. And the big idea with event sourcing is that events, not only are they used for notifications, but you actually use events for persistence. So in other words, we're no longer updating the database and publishing an event. We're just saving an event in what's known as an event store, which implies that it's published as well. So the way you would represent orders is as follows. So logically, you could imagine an event table, but in practice, there are many, many different ways of implementing event sourcing. So when an order is created, you would insert into that table an order created event. When, say, it gets approved, you'd insert an order approved event. And then when it's shipped, you would insert an order shipped event. That's how you store the state of the order as a sequence of state-changing events. And then when you need to reconstruct the current state, you would load those events and replay them and basically do a functional fold over those events to get the current state. And when you save an event in this way, it's implicitly published as well. So that's event sourcing, and it solves the problem of data consistency. There's also a problem with implementing queries in this architecture. So let's imagine that you wanted to find recent valuable customers. If orders and customers were in the same SQL database, you could accomplish that quite straightforwardly with a select statement like this. You just do a join between orders and customers with the appropriate where clause, and you would get back the data that you need. But remember, in a microservice architecture, orders and customers are going to be in different services. So you can no longer implement sort of queries like this. So getting the data that you need is quite challenging. And what's more, if you're using event sourcing in your system, then actually querying the current state of a entity is also a lot more complicated as well. Your SQL statement would have to find those events, combine them, and compute the current state. Perhaps it's doable, but your query is likely to be complex and possibly inefficient as well. So there's a challenge of querying. So the solution is to use an approach known as command query responsibility segregation. The idea there is you split your system into two parts. One part is the command side, which handles, creates, updates, and deletes. In other words, HTTP posts, puts, and deletes. And it contains the business logic that is implemented using event sourcing. There's also a separate query side, hence the term, with separating commands from queries. The query side is responsible for handling, as the name suggests, queries, or in other words, HTTP GETs. And it does that by querying a materialized view. It could actually maintain multiple materialized views using a variety of different databases to support those queries. And of course, one of those databases could be Redis. The query side is kept synchronized with the command side by subscribing to the events that are being published by the command side. So when state changes in the command side, that is of course represented as events, and those events get consumed by the query side, which then go and update the materialized view. So we've come quite a long way from our simple monolithic application with a monolithic SQL database to a much more elaborate system. But this architecture sort of solves quite a number of problems. So on GitHub, I've got an example of how to use Redis as a materialized view. So in my book, Pojo's in Action, the example application is called Food to Go, a fictitious Grubhub-like company that delivers takeout orders to customers. And as you could imagine, a key part of that application is a database of restaurants, their opening hours, and their sort of service area where they would be delivered, where they delivered to. And in fact, the service area is represented using zip codes. This was 10 years ago, and so geo-search wasn't straightforward back then. It'd be interesting to re-implement this using Redis 3.2. So in this application, I'm using to support the query finding available restaurants. I'm using Redis as the materialized view, and it's using sorted sets to represent as the denormalized representation of the restaurant database, which can very easily be queried. So when a request comes in for the available restaurants, the service actually uses a zrange by score command to find the restaurants that are available. There's also another service that's subscribing to events coming from the event store, and then using commands like zadd and zremove to keep those sorted sets up to date as the command side is changing. Anyway, I'd encourage you to go have a look at this example app. It's kind of a very neat use of using Redis as a CQRS view in an event-driven microservice architecture. So in summary, you want to break up your engineering organization into small, agile, autonomous teams. Each team is responsible for deploying or developing and deploying one or more microservices. That's how you're going to develop fast and reduce time to market. You want to use an event-driven architecture that's based on event sourcing and CQRS. And then last but not least, you want to use Redis throughout your microservice architecture. So thanks. I hope that you found this useful. So thank you.
Please welcome back Salvatore.
We could be
So if there is something different about Redis compared to other databases, is that it's not the recipe, but it's the ingredients. I believe that developers love to work with Redis because it's not a pre-cooked solution, but they are the stars. The developer takes the ingredients that Redis exports as commands, and then there is to make the recipe, to find the best way to put the commands together in order to get the solution that you are searching for. And when initially I released Redis, and there was the Google group initially where people posted solutions, there were people that were extremely good at finding solutions using the Redis commands in order to get the work done in a very strange way, like abusing the commands, but in an interesting way in order to get to the actual result with the minimal memory usage, the minimum data moving, and the best performances. But in general, the Redis community is a community about building things on top of Redis, not just using it. There are proxies implementing eventual consistent systems, like 25 message brokers on top of Redis, client libraries abstracting away what you can do with huge Lua scripting. So basically Redis is a system that's meant to be extended in one way or the other, both using the commands, but also creating new layers of abstractions on top of Redis to create new things that sometimes don't even resemble Redis. It's just a backend. But we needed to go the next step in this process to really give more power to the users to exploit Redis to a level that it was impossible to do before. So today I'm extremely excited and happy to announce the Redis modules system. The Redis module system is, as you can guess, loadable modules for Redis. What you do is to take a C dynamic library, you load it back into Redis, and you have new commands. It can export new commands. But the interesting thing is how it works, because there are two wrong ways to create a module system on top of Redis. First wrong way, to just create a dynamic loadable library that directly uses the core functions of Redis. This gives you access to everything, but then what happens? If we evolve the internals of Redis, all the modules are broken, or otherwise, in order to the module system to catch up with the changes inside the code, the developers of the modules have to rewrite the module again and again and again. Every time an API inside the code changes, the module is no longer usable. That's a terrible thing about module systems. When every time the system evolves, all the modules must be changed because something will be broken and something like that. Also, there is another way to make wrong modules. That's just to take C and export the same API that currently is available to Lua scripts. That's just call Redis commands and get the reply. This is more a form of composition. You use the Redis commands in order to move data back and forth, but you are not really extending Redis. The extension means to create a module that can do things for which Redis was completely not designed to. That's the real point. And what this means is to access to the low-level data structures of Redis, really at sea level. And so that was tricky because in the past, the only possibility was to fork the Redis code and manage your own tree, basically. And then try to catch up with upstream, merging conflicts. It's a shame, basically. This was anyway done by many large shops, because when we have really terabytes of Redis instances, at some point you say, I want really to specialize Redis for what I'm doing, because specialization can mean like to use half the CPU power compared to using Redis as it is. So it's a huge drive that makes you willing to specialize Redis, even forking the code. And so the plugin system can be a solution, but how many times you happen to see people handling modular system and saying, oh, the module no longer works with the new version, or it loads, apparently works, but instead misbehaves in one way or the other. What is the solution to this dilemma? It is possible to create a modular system that allows the access to the very low level, but at the same time, it allows the core to evolve without breaking the modules, and also the modules ecosystem to evolve without having interactions with the core. Yes, it is possible. The trick is to create a complete interface, a wrapper interface between Redis and the module system. In this way, basically, what you have is an API that mimics the API that Redis core commands use in order to implement a given command. But it's completely isolated, even the defines, the structures, everything is opaque. There is no possibility to access really like the core structures at field level. In this way, it is possible to create a modular system that a given module compiled today will work for the years to come. For example, you build a module today, thanks to the new module interface, and you want to load the same module that you created now in Redis 5.0, but the binary, I mean. So basically, the Redis module system provides complete backward compatibility both at the API level and at the binary level. And with extremely interesting features. For example, there is also the ability to call the Redis commands, the internals of the Redis commands. Like, I mean, if you want to call exists, you can from a C module, but that's not optimal. You want to use the low-level API to open a key to understand if the key exists or not. Then there is, so there is an high-level API and a low-level API. There is a stable C API with a binary interface, and the modules can be loaded and unloaded at runtime. It means that you can upgrade your Redis instance while it's running. For example, if you have an updated module version, you can use a command in order to download and load the new version, and the application will keep running, but there is an upgrade of the internals of Redis. So what you can do with modules right now is to export new commands. Basically, the module loads inside Redis and asks for a given version of the API. That's a very important point, basically, because it will be possible to evolve the module interface. But the old modules that will ask for a given version of the API will get what they expect, so they will continue to work. But this will not prevent us from creating new versions of the API of the modules if we see that the first one can be improved. Then there is an interesting feature that's called the strings DMA, direct memory access. Basically, what you can do is to create a module that returns the raw pointers to a string inside Redis. So your module can do fast C-level operations directly with pointer maps. And when it's done, it commits basically the change by closing the key, and then the change can be propagated to slaves. So basically what you can do is to implement the new data types on top of Redis using the strings as a container for the representation you want to use. Also, you can create new data types by exploiting the existing Redis data types. So you create metadata types that are the sum of the data types already existing in Redis. And there is this very important guarantee that modules that are written today will always work. I mean, there is until Redis 4.0, that's the first release that will feature the modules, will be released. There is room for changes in the API. It's not already frozen. But once the first version of Redis with the modules interface it will be released, then it's guaranteed that all the modules written starting with the new API, with the stable API, will work forever. It means basically that you can have also, for example, in your company, you write a module in order to fix a specific use case you have, and then you want to upgrade your Redis server, and you can be sure that you can keep the dynamic library in its path, and the new version Redis will be able to load it and execute it. So this is a very important operational simplification. Otherwise, there is to fetch the module source code, recompile, make sure it works, and stuff like that. But we don't want to stop here, because the ability to load modules that can export new commands is very powerful. With new commands, you can do a lot of things, also because you can create commands that are wrappers. Like, for example, I could create a command that as a first argument is my new command name, and as a second argument it's the name of another command I want to call. So I can create commands inside commands. However, we want to go a bit further and provide the following features. One is the pre-call hook. It means that a module can register a C function that gets called every time a Redis call is called. Okay? So I call set. The module gets the callback invoked and tells, do you want to capture this command execution and do something completely different? For example, I could implement an authentication system and I could deny the command or not. Otherwise, the module can say, no, I don't want to capture this execution of this command. Please go through the normal Redis dispatch of the command. Another interesting feature is the timer callback. It means that a module can register a callback that's called, for example, even 100 milliseconds. It means that in this way, modules can perform incremental work. For example, we'll check a given list in order to make the average of the latest aggregation of the latest values and put these values into a new data structure or something like that. And then there is the big question of the new data types API. In the end, we want to reach to the level that you can register basically a new data type that you can implement inside the module. For example, you want to add the tree to Redis, okay? So you start with a binary tree, for example, in your data structure, and then you fill a structure with function pointers in order to register the methods in order to store this data structure in the RDB file or to load back from the RDB file and stuff like that. You can already implement your new data types by using string DMA. For example, at Redis Labs, at test modules, we implemented an inverted index vir that will give a talk about the internal API of the Redis modules after lunch. Implemented an inverted index not using the Redis data structures, but creating a new data structure that's stored inside strings. So it's already possible, but we want to do more. Another interesting thing is the cluster API, because when you start a Redis cluster, what if the module is able to discover the topology of the Redis cluster, and also to a given copy of a module in one node can exchange messages with another copy of the same module in another node. So you basically can say, even I want to use Redis modules to build something that has nothing to do with Redis. I just use the networking, the protocol, the framework, basically, the data structures if I need to memorize things in my computation, but then I build something that's completely unrelated. A system to manipulate images, or a messaging system, or whatever I need, or an ID generator, distributed ID generator, whatever I want. Instead of creating a new project from scratch, writing a lot of C code, writing clients, you start from a foundation, and you just write the modules in order to implement what's missing inside Redis Layout in order to get the work you want. So basically, I believe that now we really open a new stage in the Redis community, because the Redis modules will be completely a bazaar model. It means that there will be a modules directory where you can register the module, but without any approval or verification process, and everybody can write its module and publish it on GitHub and implement new functionalities. It means basically that the Redis community is no longer stopped by the fact that the Redis development itself must be slow, because it's system programming. We cannot just write a couple of code and put it in production. Redis must be stable. You must be able to trust Redis, because you need the database to be extremely stable. Also, you don't need a multitude of commands modeling very vertical use cases. So the core will be the general data structures that Redis provided. Over the time, we will add generic stuff like the geo stuff, bitfield, because they are generic. But then if you have a very specific use case, it's interesting that you will find a module on GitHub solving your problem, or you can write your own. So I expect and really hope that the user base will start to use this feature a lot. We did a huge effort in order to make a C API that even non-C programmers want to use. For example, there is the automatic management of memory. When you allocate something in the context of a command execution, if you forgot to release a given value, the context remembers it, and when the command returns, it's freed automatically. This is very important. Also, there is a very clean API that can do like very low-level stuff. For example, if you have a sorted set, you can say seek me in a given element of the sorted set, and then you have a cursor, and you can do like next, previous element, and stuff like that. So we really cared about providing a clean API for users to work with modules. Not everything is already implemented. There is already a good start in order to implement interesting modules. The part of the low-level API that we still didn't have can be covered by using the call method in order to call existing Redis commands. But we hope in the next weeks to cover all the low-level stuff, and then start with the timer hooks and with the pre-call hooks. And this will be basically the big feature of Redis 4.0. And at this point we see, okay, we are happy with the API, and we will release the first release candidate. When release candidate 1 is out, we say, okay, now the API is frozen. And you will not see your module broken, changes and stuff like that. So I hope you will write some module and ping me if you have questions about the module system. There is a file I just pushed online on the Redis Unstable branch a second before going on stage, the new code. There is the documentation, and there is an example module that's called the Hello World module, where there are multiple examples of implementing new list commands, how the replication works, because the API also allows the commands to be replicated to Snake and stuff like that. reading the examples, it's pretty easy to start to get a feeling about the API and what we do. So thank you, and let me know. I'm here today and tomorrow if you want to ask questions about module system or anything else. I will be more happy to reply. And make sure to don't miss the Veer talk after lunch, because he will really zoom inside the modules API, what you do to register new commands, what you do in order to access and use the low-level API to open the key, check the value and stuff like that. Thanks.
Ladies and gentlemen, please welcome Chief Developer Advocate at Redis Labs, Itamar Haber.
Hi, everybody. First of all, welcome and thank you all for joining us today. My session today is going to be about Redis modules. I think there's nothing more amazing that happened recently other than that. This is a picture of me hearing about it for the first time. My wife was there, so she took the picture. There's also, of course, version 3.2, which got released last week, which is also amazing. This is how I look with version 3.2 out. Like, Salvatore, congrats, but Redis modules. This is what I want you to remember. Redis modules. It's been a long wait, and we dug in the archives, and we actually found that modules, the idea for modules, has been around for quite some time. If we'll take a brief dive into histories, folders, and I ask you not, it's a real screenshot, by the way. You can see the date up there, August 9th. It's the first release of Redis version 1.0, and someone suggests there that it could be, and another interesting idea is to add support for plugins implementing specific commands and associated data types. So the idea was out there for a long time. It just took some time to get here, and Salvatore mentioned the challenges, and there are real challenges in implementing that. But the models are here, and what I want to do now, before we release you guys, and having sat so silently throughout the thing to your break, and after the break we'll continue with all the good stuff that we've prepared, are the 3 steps that each of you needs to take in the road for building your own modules. So the first step, and perhaps the crucial one, the most important one, is to dream it. If there's any feature that you've ever wanted in Redis and you didn't have it, or if there's a wild idea that you're just dying to implement, you need to come up with the idea. We can't help you with that. What we can help you with are the next steps. There are 2 other steps you need to take in your road to moduling. The next step is actually build it. You can go to the GitHub repository. Salvatore pushed to unstable the latest modules release and play with it. It's not final. The final API, the final release is still to come, so things are up to change, but you can build it. We've set up and started an SDK that you can just pick up and start using to write your first module. There's the Hello World example that Salvatore has prepared. The SDK will make your job a lot easier, and we'll be pushing more and more stuff to help you as time moves on. But the third step is perhaps the most critical step, and this is what I like to focus on right now. It's ship it. You've dreamt it, you've built it, now you want to ship it. Sure, you can use it yourself, but it's fun sharing. Modules are built to be shared. And Salvatore mentioned it. We are going to have an open source modules sort of thingy on Redis.io. It's going to be a huge place. Every open source model can just go up there. The process that we envision, and it's a process in the making, everything is still being developed as we speak. So the process is that anyone can upload his open source model, just link your GitHub repository and you're done. We'll have some automated checks there, just some sanity checks, but it will be open for everyone. The community will filter it, basic filtering, perhaps some social capabilities. And as I've mentioned, it's still being developed. You're welcome to help us with the development, pitch in on ideas, just, do your stuff, you're the community. This is the open source modules place. Redis Labs is also setting up a hub, a modules hub. It's actually online, so you can go there and browse. There are a few modules, that we've set up and uploaded. We'll be speaking about them throughout the sessions. Veer will show you, as we mentioned, right after the break. We'll have a workshop on how to start building your module, and tomorrow I'll be picking up with that with Iftach as well. So go there and see what we've prepared for the lunch for you. The hub, the modules hub by Redis Labs, is going to be also accessible to anyone and everyone. The main difference is that it will both show open source modules and commercial modules. And what it offers, the main differentiator, is the fact that we're going to certify, verify each and every module that we'll put up there, because all the modules in the hub will be available throughout for consumption through any Redis channel, be it the open source channel or our very own Redis Cloud and Redis Labs enterprise clusters will support the modules on the hub. So, this is how it looks like, by the way, a screenshot, at least from yesterday, so it may have changed drastically from yesterday. But again, it's up online, or should be. We'll just open it. Browse overs. Modules, you need to remember that from today, and remember how to react appropriately. Have a great break, guys and girls. Thank you for attending us, and we'll meet you after the break.